Welcome everybody to yet another installment of our Closer Look Journal Club. It is our great pleasure to have Cohen today give a talk on probing local nonlinear viscoelastic properties in soft materials. I'm really grateful to my co-hosts Emma Lejeune, Matt Bursey, Johannes Weickenmeier, and Adrian Buganza. And because Tal asked us to, we're keeping the introduction very short. And I'm handing it over to Tal, and I'm looking forward to his fantastic talk.
Yay. Thank you. Thank you, Manuel. And thank you so much for inviting me to be here. I'm going to talk to you about this paper, and I'm going to initially give you the motivation and kind of the framework that we were going for in trying to probe the local nonlinear viscoelastic properties of soft materials. And then I'm going to hand it over to Cohen, who actually did the work, and he's going to tell you how we actually did that. And so let me dive directly into the motivation. And here's you can see Cohen did much of, and Tomas also did much of the work in the theory side of the work. Christine did a lot of the experiments that we're going to show. Okay, so let me dive right in. And when we, from our experience in the lab so far, when we try to probe the properties of soft materials, we always have a lot of trouble. If it's the basic uniaxial test or the shear test, these methods were developed for metals and for stiff things. And when you try to apply them, they're not readily, they don't really actually work well when you take it for very soft and biological materials. Even if you can manufacture a very, very nice synthetic dog bone shaped sample, it doesn't always work well. There's slipping and all kinds of issues that come up. When we talk about biological materials, we're also very well aware of the fact that once you remove them from their natural environment, you immediately degrade their properties, and you're not going to measure the right in vivo properties. And there's also then the effects of all kinds of heterogeneities and things like that. So we've become very motivated to maybe find better ways to probe material properties, but beyond the fact that the current methods aren't just perfect for it, are really like another very important motivation that we have is maybe that we can actually begin in the future to use this for diagnosis. And the practice of feeling someone's tissue in order to distinguish between stiff and soft regions or different type of rate-dependent behaviors of tissue is called palpation in medicine. And it's a very ancient practice. It actually dates back to the ancient Egyptians, and you can find in their recordings of all kinds of explanations of how to do diagnosis by feeling tissue and feeling different organs out. And traditional Chinese medicine also recorded a lot of these kind of practices. So it's really kind of well known and acknowledged that different diseases present by changing stiffness and rate-dependent properties of tissue. Quite interestingly, and to me very surprisingly, in modern medicine, we've only started to do this in the 1930s. Before that, it wasn't considered respectable to go and feel out someone's tissue. But since then, it has exploded, and even when we go to any regular exam, the doctors would feel our tissue. And it's been considered a very effective method to detect for early detection of tumors and other pathologies. And many of us are instructed to do this regularly to ourselves. But for me, even a more strong motivation is that it's also used in surgical rooms. So when breast cancer when a surgeon attempts to remove breast cancer, they would actually open up the breast and feel out the tissue in order to identify stiffer regions. But this is imperfect. Doctors are subjective in the way they sense stiffness. They have gloves on their hands. And what it leads to is a lot of misdiagnosis or repeat surgeries. In case of breast cancer, roughly 30% of patients would require repeat procedure. So we've we really think that understanding how to measure in vivo properties of soft tissue has huge potential. People that developed the method called elastography have also identified this potential and have been successful in applying it in certain scenarios. This is a method by which you use ultrasound or MRI to identify displacement of tissue, but it is also limited because of the basic assumptions that they have to make. The approach that we've become very excited about is essentially based on cavitation rheology. Let me just stop for a moment and emphasize that what we think we need is a minimally invasive method, but something that would remove the subjectiveness of feeling out things with our hands to bring modern medicine some quantitative measure for palpation. And so this promising approach that we see is cavitation rheology. From my point of view, an ingenious idea developed by Al Crosby's group at UMass Amherst several years ago. And they have this really, really simple idea. We often use syringes in biological tissue inside surgical rooms and in other places. Can we just insert a syringe into the tissue, eject some fluid, and use that method to measure material properties? And what they suggested is that we know that there is this instability that happens in materials when you expand a void in them, or a bubble, as you can see here from this sequence of images. What they're doing, they injected a needle into some soft, transparent material in this case. They inflate a little bubble at the tip of the needle, and they look at how it expands when they're controlling the pressure. So you see this linear increase in pressure over time. But what you find is at a certain instant, suddenly this bubble just spontaneously expands. They think of this as being a cavitation instability, and they can capture from their experimental system this critical pressure and relate it directly to the elastic modulus of the system through theoretical formula. And this technique has been applied actually quite broadly, and also shown to work for biological materials. And they use this method actually to show the degradation of elastic properties in vivo versus in vitro. So we see this to be a very promising technique. However, it hasn't really lifted off and gained traction to be as a more conventional technique, even though it has been available for over a decade. And we think that that's because of a number of caveats. And to explain that to you, I want to just give you a brief kind of understanding of what this cavitation instability is. So let me just kind of talk to you just for a moment about cavitation theory. And you can see here at the corner of the screen, a hole. Imagine the entire white region here being a solid, and you have this hole in it, and you're applying increasing pressure at that hole. You can define the stretch in the material, the radial and circumferential stretches. This lowercase a would be the deformed radius of this cavity, the uppercase a, the original size of the cavity. And if the material is incompressible, the kinematics, the deformation is fully defined, and you can go directly to calculate what the pressure would be for a given energy hyperelastic model with a free energy function. For the case of the Newtonian, it reduces to this, it integrates directly to this very simple form. So you can find the pressure as a function of how much you expanded this radius. And I can plot this for you here. And you can see that as you're increasing the stretch, the hoop stretch, essentially increasing the size of the cavity, the pressure increases. But according to this formula, it eventually arrives at this asymptotic value of 5/6 E. Notice that this is normalized. And this is what we call the cavitation instability, because what it says is that there's a certain critical pressure that you can apply within this cavity that would cause it to expand spontaneously. And you don't need to further increase the pressure at all. An interesting thing, though, is that here I was kind of considering an infinite medium. If the medium is not infinite and has, even if it's relatively large compared to the size of the cavity, eventually you won't arrive at an asymptote, but a maximum value. So you would see some discrepancies here. But most commonly, people would assume the medium to be infinite and think of this asymptotic value as being a cavitation instability. And what I want to take away from here are two main points that have driven our own probing technique. One of them is the fact that if you have this kind of asymptotic behavior, or in a more realistic sense, a maximum pressure, you cannot control the pressure. And so a pressure-controlled experiment kind of fails. You might be able to find that critical pressure that they find in the cavitation rheology technique and infer something from it. But then when you look also at the size dependent, it's not really clear what pressure you might get. And this size dependence becomes quite large even at moderate strains. But regardless, what we do find, and this is an important point that we take in our method, is the fact that regardless of the size dependence or maybe other effects that could emerge at these very, very large deformations, there is an early part that is completely insensitive and all of these curves collapse. And we're going to take, and this goes all the way up to moderate stretches, and we're going to take this part of the response in order to understand the material properties. And that's where we come to our volume controlled cavity expansion, in contrast to pressure controlled. It allows us to track that curve fully instead of just identifying the critical maximum pressure that they were able to probe in those earlier tests. And so the person who worked on this in the earlier version of our volume controlled cavity expansion method was Shabnam. She put a lot of effort into developing this method, and there were some unexpected things that we need to handle. Well, the first thing was we needed to eliminate any compliance in the system so that we can fully control the volume. This was not trivial to do. We ended up mounting the syringe system on an instron, which gives us very high control, and making sure everything is very stiff compared to the stiffness of the material that we're probing. But in doing this and removing all of the different tubing and things that would have been in a different, more complicated system, our only measurement was this motion of the instron and the applied force within the syringe barrel. And that required then calibration to remove the frictional force in order to actually understand from the measurement of the instron what the pressure is inside the barrel. And that calibration is kind of what you see here. And then another caveat in our technique, if we actually want to capture the pressure, the constitutive response, the pressure volume response, we need to know what at least an effective initial volume is, or what the size of the initial defect that we made the material, that we made in the material in the process to obtain a measure for the stretch. And that is something that we did through a fitting method. So all of this was done by Shabnam. And then when we started to work on the paper that we're going to talk about today, the idea is, can we take this idea and transfer it to also understand rate-dependent viscoelastic response? And so to do that, we initially and when Christine started to set up experiments for this, we were wondering if this is actually even possible, or is it like a completely impossible mission? And there's some reason that we were very confident that we can do this. One is that we were able to show that our VCC technique was relatively high precision compared to other techniques that we saw. I'm giving here just two examples, comparison with the cavitation rheology method and other rheology and indentation methods shown in a recent study in brain tissue, shows that our VCC method actually performs quite well with very small error margins and uncertainties. This is another comparison here, and you can see very little scatter obtained from the VCC method compared to other techniques. So we think in that sense, it could be a good platform to begin to look at rate-dependent properties. Because we're controlling the volume, we don't have additional issues such as overestimation and fracture that other needle-induced methods exhibit. We don't need visual tracking because we're controlling the volume. And we've even been able to use this to transition into fracture. The most importantly, with our motivation to drive this into medical diagnosis is the fact that it is very minimally invasive. So these are the merits, but there's something that might not work. And that's what troubled us initially. Even all of this proof of concept experiments were static. So why would it actually work in a dynamic sense? This friction correction that we were doing, it wasn't really clear how we would do that in a dynamic test. And most importantly, even though we have quite nice accuracy already, when we're looking for viscoelastic properties, we're not looking just for an elastic modulus, we're also looking for small changes in that elastic modulus over time, which requires much higher accuracy. And so this is what the type of issues that we had to deal with in this work. And what I'm going to do now is hand it over to Chokalingam, who's going to tell you how we actually achieve this in this paper. So I'll let him take over.
Hi everyone, I'm Chokalingam. I'm a graduate student working with Professor Cohen. So I'll be presenting the rest of the slides today. So first I'll present what were some of the improvements we made to the experimental setup itself that gave us like the precision and both the pressure and the volume control that allowed us to do the rate dependent testing. The first change we made from like our previous VCC work was we went from like a static testing machine to a dynamic instrument that gave us more precision in the movement and control for like a dynamic loading. And the other thing we realized was, since the testing machine has like a fixed precision in terms of its vertical displacement, if we reduce like the size of the cross section of the needle, that allows for more precise volume control, because the volume we inject into the solid is basically the area times the displacement of the plunger. And what we see is that when we were typically using 3 ml syringes, which are quite fat. When we go to like these gas tight syringes that are extremely thin and have like this 50 microliter volume, there's a significant improvement in the volume measurement error and consequently the effective size of the cavity. So that already gives us like high precision for the measurement of the cavity size. But in introducing these gas tight syringes, they also introduce like high friction. So the earlier way of measuring the pressure by measuring the force in the testing machine was not as reliable. So instead we manually added like a pressure sensor in series with our equipment here that you can see here. And that directly allows us to measure the pressure. But we also do some correction to measure the pressure drop in the syringe needle here, because we want the pressure applied on the cavity wall. So based on the flow rate, there will be some amount of pressure loss here, which we calibrate for using some calibration experiments. And we also correct for the surface tension effect between the fluid and the solid. And so these additional changes allows us to measure the pressure and the volume with very high precision. And so the only thing that remains to be done is to figure out a way to use this to extract the viscoelastic properties of the material. And so that's what we did next. So we basically did a lot of testing and arrived at the cyclical loading protocol at the end that allows us to probe the material at multiple stretch states within a single probing. And schematically, this can be represented in this way. So we start at a relaxed cavity size A1 at some relaxed pressure P or PS. And then we expand the cavity at a given fixed cavity expansion rate A dot all the way to a size A2. And then we just fix the cavity size at that larger size. And then we just wait for a long time. And we'll see that the pressure starts to relax. And this is basically due to viscoelasticity. And it'll relax all the way and it will stop at some value, which is the relaxed equilibrium pressure at this cavity size. And then once again, we start retracting the needle at a very slow rate to go back all the way to the initial cavity size that we started with. And then again, we wait for a long time at this cavity size, and we'll see that the stress starts to recover back to the value we started at. So in essence, this is kind of like a stress relaxation experiment in a cavity expansion setting, whereas this part of the curve is like a stress recovery experiment. And typically these are done in uniaxial settings, but here we do it in a cavity expansion setting. And this is like one cycle of loading. And so we repeat this cycle for like multiple different expansion rates, meaning different rates at which the cavity size increases. And that allows us to do multiple cycles of loading by just like a single probing of the same material. But the retraction is always at a fixed small rate because we don't want the serums and the fluid to separate. But for the expansion rate, we double the cavity expansion rate between every cycle. We are also, before we do this, we also take care of some things to make sure we have some repeatability and precision in the experiments. One thing we do is like, we predetermine like an expansion range in which the material doesn't fracture, and we limit our testing to that range so that we don't have to deal with the fracture process, and we only are probing the viscoelastic response. And we also remove this Mullen's effect, which is basically a softening effect, and which we observe in soft rubbery solids, whereby when you load the virgin material for the first time, the response will be quite stiff. But when you unload it and reload it again, you'll observe some significant softening. And if you keep cycling the material, within a few cycles, you'll see that the material response actually starts to coincide. And we showed this effect in the cavity expansion setting. And to our knowledge, this is the first time that's being shown in this setting. Typically, it's shown in like a uniaxial loading. But basically, I'm just showing all this to make sure. So we basically pre-cycle the material in the stretch range that we want to test to remove this Mullen's effect. And then that's when we start the testing and do this loading protocol basically. And so here I'm first going to show some results of this loading protocol applied to a very soft PDMS sample, which we consider here as like a proxy for biological tissues. And so we basically do the cycling at different expansion rates. The slowest rate we work with is like 0.01 millimeter per second, and the largest rate is 0.32 mm per second. And these correspond to stretch rates of about 0.01 to 1 per second. And we can already see, I'll note some observations from our experimental results here. First, this pink curve at the lowest rate, we have actually plotted the results for 3 cycles. So we repeated this loading 3 times, and we see that the curves actually exactly overlap with each other, meaning we have like high precision in the pressure measurement, and we also have like high repeatability because we can't even see the curves being separate from each other. So it's like very precise in that sense. And we can also see that there's a clear rate dependent effect where the pressure clearly stiffens based on the stretch rate that we are working with. And there's also significant viscoelastic relaxation when you hold the stretch constant. So all these are indicators for like significant viscoelastic response. We can even see the pressure relaxes from its maximum value by almost 40%. So this is not some negligible rate dependent effect. The other thing we see is like, so irrespective of the stretch rate that we loaded, when we wait significantly long enough, the pressure that it ultimately relaxes to is always almost approximately constant. So this relaxed equilibrium pressure is highly repeatable, and we will later use these repeatable pressures to extract the elastic moduli of the material. And this pressure response is basically the equilibrium elastic response of the material after all the viscoelastic effects have died out. So we use that to extract like the purely elastic part of the material response. There is some slight drop in the relaxed pressure across when we keep loading the material, and we attribute that to some probable fatigue, but we do not account for that in our modeling here since it's kind of negligible. And so one thing I want to emphasize is one key aspect in the loading protocol that enabled us to like visualize this viscoelastic effect is the fact that we actually control the cavity expansion rate, whereas most cavity-based methods, including cavitation rheology and our previous VCC tests, they were doing like a constant volume rate injection. And I later show why that might not be that conducive and like elucidating or eliminating this viscoelastic response of the material. But before I do that, let's first see like how we extracted the viscoelastic properties from experimental results that look like this. To do that, first we obviously need to like describe a constitutive model for the material. And to do that, we use like a generalized Maxwell model where we have like an equilibrium elastic branch and multiple non-equilibrium viscous branches. And the motivation for choosing a model like this is we did see from the experiments that when we wait long enough, the pressures relax to some equilibrium value that depends on the stretch, which will be captured by this branch, whereas the rate-dependent effect will be captured by then viscoelastic branches. And depending on how many branches we need to fit the data, we can have like one or more branches here. And so here we quickly have the constitutive model itself. We decompose the deformation gradient into elastic and viscous deformations. We additively decompose the free energy for each branch. This corresponds to the equilibrium elastic branch that will capture the purely elastic response, and the other branches capture the viscoelastic response. The free energy will give us the Cauchy stress. We assume that the material is incompressible, which is often a good assumption for many biological materials, and especially since we are working with PDMS here, that's a good assumption. And then we need to prescribe a kinetic evolution law for how this viscous deformation tensor evolves with time. And this is something that we can choose, and it's a constitutive prescription. It just needs to satisfy some basic things like frame indifference, the second law of thermodynamics, and so on. And we tested like many different laws, and we arrived at this final law, which gave us like the best fit for our experiments. But we are free to choose this depending on the material that we are testing. And once we have the constitutive model described, we need to develop the equation of motion for this boundary value problem, since we are like expanding a cavity. And if we run through the motions, we can arrive at this equation, which basically relates the pressure at the cavity wall to the motion of the cavity itself, where lambda A is the stretch, the circumferential stretch at the cavity. And we also have multiple different components here. So this is the contribution from this purely elastic branch. This is the contribution from these non-equilibrium branches. And they have like this viscous hoop stretch in them, whose evolution will be decided by this evolution law. And then there's some very negligible inertial effects, which have some slight effect when we go to the higher expansion rates, but overall they are much negligible compared to these other terms. And so this is for like any general free energy psi. And here we work with neo-Hookean free energies, which works well enough for our PDMS testing. And the equation of motion specializes in this form. And these are basically the parameters that we need to fit for. E is the Young's modulus of the equilibrium elastic branch. These alphas are basically the ratio of the moduli of the non-equilibrium branches with respect to the equilibrium branch. And then these taus describe the viscous evolution for the nth equilibrium branch, where they describe the time scale over which the stress is relaxing approximately. And we also need to fit for this parameter A, which is the initial stress-free size of the cavity or the defect. And since that's something we don't exactly control, that's also something we fit for and get out of our experimental results. And so since this can potentially be like a lot of parameters, we just don't want to do brute force fitting. We want to like isolate the physics and then use the physics to like independently fit the parameters. And as I already told you, we observe like repeatable relaxed equilibrium pressures, which correspond to this equilibrium elastic branch. And so we want to use that component to fit for the modulus A. And we do that by zeroing these components. And so we have two pressures, so that gives us two equations for E and A. And then we do like a nonlinear least square method to fit the dynamic response to get the other parameters, the viscoelastic parameters. And we basically first start with like one branch to see how good the fit is. And then we keep increasing the number of branches to see like how many we need to arrive at a good fit. And for the experiments here with PDMS, we see that using two non-equilibrium branches and one equilibrium branch, using like a single set of parameters, we are able to like model all these stretch rates quite well, where the maximum error at any time is like under 7%. And so here we have the fitted results. The dashed lines are our model prediction. And this is like the pressure time curve, and this is the pressure cavity size profile. And so here I'll even, so this is zoomed in only for a short amount of time. This is for the pressure time response for the whole experiment. And we can see that the fit is quite good using like a single set of parameters. So not only are the experiments kind of good, like the model is also able to capture the experimental results well. And now we also want to see like, okay, if we enter, like, is the model sensitive to like changes in viscoelastic response of the material? And to do that, we use the system where we use the soft PDMS sample, but we also introduce silicon oil by different weight percentages. So here we have like multiple different PDMS samples where we kind of fix the base to cross-linker ratio, and then we increase the amount of silicon oil inside this PDMS. And we see that, so this was an experimental system that was already used by another group. So that was our motivation to do this. And we do see that our experimental method is sensitive to capturing the changes in the viscoelastic response. The more silicon oil we introduce, the viscoelastic stiffening with the stretch rate kind of reduces. And when we do the fitting for the viscoelastic parameters, we see even in the fitted parameters, they also reflect this change. Basically, the alpha values for these non-equilibrium branches go down, meaning the contribution to the stress from these dynamic branches kind of goes down when you increase the silicon oil content. And that means the viscoelastic stiffening will reduce even if you have like higher stretch rates. And so we have a kind of established that this technique not only works well, it's kind of precise and it's repeatable in the sense that even while doing multiple cycles, we get like repeatable curves. And it's also very sensitive to picking up changes in the viscoelastic response. So we expect that the technique should kind of work out well even for biological materials. And we currently have people in the group trying to do this for blood clots, and Professor Manuel is also helping us with the preparation of these blood clots. So before that, I earlier remarked kind of that one important factor that helped us to visualize this viscoelastic response was the fact that we used a constant cavity expansion rate as opposed to a constant volume expansion rate. And I'll expand more on that now because it also leads us to another important conclusion. So here I'm plotting the cavity expansion rate as a function of the cavity size. And these are just constant cavity expansion rates. And obviously, so the stretch rate is just going to remain constant. But if you use a constant volume expansion rate, even if you think the volume expansion rate is very small, when the cavity size is extremely small, the stretch rate is extremely high. And there's like but the stretch rate quickly goes down as you expand the cavity. But there's like a large variation in the stretch rate through your experiment as you're expanding the cavity. And at the very small cavity sizes, even when you're using very small volume flow rates, your cavity stretch rate is extremely high. And what does that manifest in terms of the cavity expansion problem? So here I'm like numerically solving for the pressure as a function of stretch using the viscoelastic parameters that I fitted for our experiments. And these are the pressure profiles you would get if you use like a constant cavity expansion rate. And these are the profiles if you would use like constant volume expansion rate. And you can see that though the material is clearly viscoelastic, and we are able to clearly see that when we use this loading protocol, if you use the constant volume expansion rate, the response almost looks quasi-static. And this kind of falsely leads to the conclusion, like if you just did the experiment using this, you would think, oh, this is like small volume flow rates and we are seeing repeatable overlapping pressure curves. So you'd assume that it's quasi-static and you try to fit this to get like a modulus, when in reality, it's not really quasi-static. And the reason you get this overlap is basically when you go to like high stretch rates, these dashpots kind of become, the dashpots get zeroed out. So you effectively have like multiple springs and series. So you have like an effective Young's modulus. That's the sum of the moduli of all these branches. And that's kind of the modulus that you will measure. And that will be an overestimation of your elastic modulus, because technically this is really your elastic modulus, whereas this is more like a stiffened dynamic modulus. And so this leads us to like concluding that you need to be careful when you're doing these cavity-based methods, and you should probably not use constant volume flow rate, and rather use constant cavity extension rate, because then you'll truly know when you approach the quasi-static limit, because when this becomes very small, these curves will truly become repeatable. And that's not due to some, that's not because you're like in some viscoelastic stiffened regime. And so with that, like I'll conclude the talk with the key conclusions or the takeaways. So we have like established like a minimally invasive experimental method that allows us to like probe local, nonlinear, and viscoelastic properties in soft materials. We are currently working on trying to implement it for biological materials. Some issues that we potentially think might arise is like, for example, if we are working with blood clot or something, like if we wait long enough to measure the viscoelastic response, there might be some diffusion of the fluid into the blood clot. So these are things that we need to address in expanding the method. But we do show that at least for the PDMOs, it's like quite precise and there is some repeatability, and the technique is quite sensitive in picking up like changes in the viscoelastic properties. And we also showed that it's important to choose your loading protocol, and it would be better to probably use like a constant stretch rate as opposed to like a constant volume rate. And hopefully if everything goes well, we should be able to show this technique works well for blood clots and maybe other biological materials in the future. And with that, I'd like to conclude the talk.
That's fantastic work. Thank you to both of you. Obviously, I have an invested interest in the work on blood clot working out.
Thank you. We went a bit over time, sorry.
That's all right. We'll make up for it. We'll just talk really fast during the discussion. With that being said, any audience questions? Anybody have questions for Tal or her student?
Yeah, I have a quick question, sort of in the spirit of this journal club. Could you all comment very briefly on what the most challenging part of this whole setup was? Like if there's sort of one thing that was the hardest to figure out, I'd love to hear what that is, just out of curiosity.
That's a good question.
I think I would say like coming up with a loading protocol, like though we are presenting the final result, that took like a lot of time because we need to figure out like, first, we didn't realize that Mullen's effect was playing such a big role. And like, we also realized that we've actually ended up that we needed to go to like a big cavity size and relax at that value and then do the experiments from there. Because the more spherical the cavity is, the more reliable the experiments were. So we realized that going to this initial relaxed spherical cavity and then doing the experiments was an important factor. And also realizing that we shouldn't go into like the fractured zone, and like how to come up with like a single technique that's like probing all these different rates, and then coming up with like one package routine that like implements all these things was probably the biggest challenge. And the other thing was like, I guess, experimentally removing the errors in terms of like what's like the dynamic calibration that we need to do, and like how do we correct for surface tension so that we ultimately end up with these repeatable curves when we are doing like multiple cycles of loading. But maybe Tal can explain.
Another thing I think is making it that the experiments are not an art that just one person can do them, and Christine worked looking at lots of different types of needles and pointy needles or not pointy needles and different ends and how to do the injection in a very consistent way. So that we could be streamlining the technique and actually using it and teaching other people to apply it and not just have it like an in-home thing that some of us can do and others don't. Yeah.
Fantastic, thank you. I see there's other questions already.
Hi, I really enjoyed your talk. I was just wondering, moving forward, many years in the future, wanting to apply this in a clinic, potentially. You gave the example of breast cancer at the beginning. And so I guess my question is kind of twofold. Like, how do you probe the entire breast? Like what's your like length scale that you're working in to detect whether there's a tumor if you don't know where it might be? And then B, like, how do you think anisotropy, my understanding there's like a lot of collagen fibers around a breast tumor. How do you think that that's going to affect your method? Wondering if you could just comment on how you see that.
That's a really good question. So for we wouldn't for breast cancer, our thinking is not to use it as an early diagnostic tool, but actually intraoperatively. The doctors have trouble actually identifying where the tumor is. And in terms of, so you asked about anisotropy, but there's also heterogeneity, right? And then we wouldn't be probing the entire breast, but we would be able to locally inject in a number of different places, getting an understanding of distribution of stiffnesses, right? Not just one bulk measure of the stiffness. For anisotropy, we actually have some stuff we've been thinking about, and Chokalingam has been thinking about how we can maybe use a slightly different approach to look at anisotropy with a spherical cavitation. That's not going to be probably a solution. So, but we have some ideas on that, but that's kind of really preliminary.
Actually, just to update on that, yesterday, me and Gian were discussing, and even with the spherical, it's possible, but we would have to be visually able to track the cavity. So if we are able to visually track the cavity, we can look at how it's expanding in different directions to get like some directional sense of the moduli. But that would clearly not work if like we are just having like a volume measurement. So for that, we are thinking of another different geometry that we are currently working on, but it's in a very preliminary stage. Yeah.
Yeah, so we have thoughts of that. Did I answer all of the parts of your question?
Yeah, thanks. I was just kind of wondering like how you guys were thinking about that moving forward. So thanks.
Thank you for that question. Thanks for the answers. I think Saurav was the next one who had a question. Please go ahead and ask a question if you feel comfortable.
Yeah, thank you. Nice work. Excellent presentation. So I had a question regarding the testing of soft solids at high stretch rate. I mean, you mentioned there's a difference between the testing at a constant cavity expansion rate and the constant volume expansion rate, but how are you going to achieve the testing at high stretch rate with the current setup, I mean the cavity expansion rate?
So you're asking, can we go even much faster?
Yeah.
Yes. Yeah, that's a great question. And we have been pushing it as far as we're constantly trying to push more. The one issue that is that we once the flow becomes complicated, then that could really make our calibration difficult. So we don't want to push too far and start to get bogus results, but we're trying, and I'm not sure yet if we'll be able to go much faster, but we hope we will.
Okay, thank you. And another, just out of curiosity, so when you are inserting the needle inside the PDMS sample, so is there any initial fracture that is caused by the needle insertion? And if yes, then how are you going to account for that? How did you account for that?
So we're actually generating a defect when we inject. the needle into the material. And we need a defect. And that defect is approximately the size, the radius of the needle. And you can call it a fracture. We generated some damage. You can call it by different names. So I'm not sure if that answers your question.
I mean, there's a defect, but yeah, I mean, that is, I mean, inherent or something like that you're trying to say.
Yeah, I'm not sure if I follow the question then.
Okay, yeah, no problem. Yeah, thank you very much. Yeah.
Thank you very much. I think the next question was from Ali and then David, I believe.
Yes, hello. Thank you for your very interesting presentation. I'm Ali Alai from Leuven in Belgium. So I'm curious if you have any idea how is it possible to measure the porosity of the soft tissues? Because you know that most of the soft tissues has porous properties, like cartilage, for example. So is there any possibility to use this method to measure these kind of porosities in the tissues?
So you're referring to poroelasticity where you would have migration of fluid?
Yes.
Yeah, I think there are ways to look at this. We have thought about it, but not yet looked into it. One thing, for example, that you could do is inject a miscible fluid and then see how long it takes it and probe the pressure as it is diffusing. We haven't looked into that though.
Thank you very much.
David, I think
actually my question was pretty much along the same lines. I was curious about whether or not you guys have thought about, I mean, obviously with PDMS, you don't have to worry about the fluid leaving, but in any tissue, you'll have some porous transport of that fluid when it gets injected. Have you guys done anything yet on that? Or is that kind of then a next step when you sort of port to tissue?
Yeah, it's kind of interesting. Even when this question kind of reminds me when we were starting and developing this technique, we did everything we can to avoid fracture. And now that we have this technique set up, what we're looking at is to see what happens when you actually continue and move into fracture, right? And now another thing we were avoiding with all our might with these experiments is diffusion, because we want to control the volume. If the fluid is diffusing, we don't want. That's going to ruin our technique. So we were doing everything we can to avoid diffusion. We would have an immiscible fluid, or really thinking about that a lot and measuring, making sure that we actually have all of our fluid with us and we're not losing any. But now that we have everything set up properly and we know what we're doing, we have been thinking about that effect. And can we use this to learn something new about materials? Or maybe in terms of probing, sometimes it's more convenient to use water, even though it could diffuse. So then there's this rate competition. You can maybe do a very fast test and get pretty good results without worrying too much about diffusion, as long as you're in a certain time scale. So we've been thinking about this a lot, but it really reminds me like that this is just like something that we've been avoiding that now we're going to actually try to do. So. But I don't know if that answers your question.
Yeah, it does. Yeah. Thank you.
Thank you, David, for the question. Any other questions? If not, one of the things that we always do though is because we send a little questionnaire beforehand with potential questions that they have time to prepare for, that we believe may be really helpful to students and postdocs that are listening in, or junior faculty that are preparing to become faculty themselves. And one of them, Tal, was you used to not be an experimentalist, if you're not entirely mistaken, and you started a faculty job and chose to do experiments. And we were wondering whether you wanted to share with us what your thinking was in terms of why make that investment and take a little bit of a risk there, and also what was the hardest part of making that transition.
That's interesting. I actually started the faculty position as a pure theoretician. So my startup package did not include any experimental facility. And I was really confident about the fact that I would just collaborate with all of you fantastic experimentalists and it would work well. And what I learned really quickly is that works really well when they're really complicated experiments, and that a lot of the research is driven from the experiment, and then there's need for theoretical reasoning. But when the research is driven from the theory, which is what is happening a lot in our experimental lab, it's really hard to come to an experimentalist and tell them, listen, I have this really simple idea. All I need you to do is do this very basic test and get the experimentalist excited about it. So what I found is, like, if we can do it ourselves, we must. I think it was a huge mistake for me to come in and not acknowledge that early on as a faculty member. Like, I should have had some experimental stuff in my startup package. I was under the impression that that would just weigh on me even more because I had very little experience, but I was lucky enough that the department was supportive of me becoming an experimentalist. But I think this was huge luck, like a lot of luck playing there. So if anyone here is getting faculty negotiating your package, even if you're a theoretician, ask for a high-speed camera, ask for some basic mechanical testing, some space. It wouldn't hurt.
I appreciate that perspective. If I can share from my own, I actually also came as a non-experimentalist, but I guess I did the opposite leap where I was like, I either become an experimentalist or I don't take a faculty job. So in the end, it came down to like who was silly enough to give me an experimental startup, even though I didn't have any experimental experience, and enjoyed it hugely as well. But that's very interesting. And I like that perspective that it matters how your experiments are driven from a modeling perspective.
Yeah.
Thank you for sharing that. Any other last questions? We have a couple minutes left. We don't need to run this all the way to the full hour, but if there are questions, I wouldn't want to take anybody's opportunity. Alessandro, please go ahead.
Yeah, hi, it's Alessandro Giudici from Maastricht University. I was wondering, first, thank you for the great talk. It was very splendid work. I was wondering how this technique could work in tissues where, like, for example, highly collagenous tissues where collagen might behave differently in compression or tension. So we might be interested more into the response to stretching rather than compression. So you can comment.
That's a really interesting question that you're asking, because you, if I understand correctly, are thinking of the cavitation experiment as a compression, right?
Yeah, exactly. Yeah.
So that's a very interesting thing that that different people see cavitation as being different things. And some people would think of it as a tension experiment, actually. And if you think about it in contrast to other more conventional methods, what we have is that in the radial direction, we are compressing the material, but in the circumferential direction, it is being extremely extended in tensile loading. So we're actually, because this is a non-trivial stress state that we're subjecting the material to, and that's why we're sometimes seeing very different behavior. We're able to exceed the values of stretch that you might get in a common uniaxial test. It's really just a more complex stress state. So you can think of it more as an equibiaxial tension test where you're applying compression out of plane. But I actually think that the more dominant effect here is the circumferential tension. So in that sense, maybe or not, maybe this answers your question. This is applying both tension and compression, but in different directions. And so in that sense, it might be better adapted to capture complex material behavior.
Oh, yeah, thanks. Yeah, that answered my question. And yeah, congratulations again. It was really great.
Thank you.
Awesome, Tal. I think it worked out perfectly with the time. Thank you, everybody, for being here today. Thank you, Tal.
And Chocolingam.
You as well, exactly. And everybody for joining us and all the great questions that were asked. I'll see y'all next week.
Thank you. Thank you, everyone.